In this video, I'm going to talk about an environmental problem that has been largely solved over the past 30 years called stratospheric ozone depletion. Surprisingly, this topic's not covered in the course textbook, even though it has quite a strong connection to energy and the environment, mainly through our use of refrigeration systems. And we talked about refrigeration systems in a previous lecture in this course. So I thought this would make a very good video lecture. Ozone destruction is caused by chlorofluorocarbons, or CFCs, and other man-made chemicals. Collectively, this group of chemicals are called ozone depleting substances, and I'll talk about that later in this lecture. I've shown one molecule here. This is CFC 11, a particular type of CFC. It consists of one central carbon atom, a fluorine atom, and three chlorine atoms. And as I'll discuss, the problem, or the environmental problem, is with the chlorine atoms. CFCs are not naturally occurring. They're man-made, so their presence in the atmosphere is entirely due to manufacture by humans. Prior to about the 1990s, these chemicals were widely used as refrigerants in air conditioning systems and refrigeration systems. They were also widely used as the propellants in aerosol cans, so everything from spray paint, hairspray, even underarm deodorants. CFCs were also used as the blowing agent for plastics like styrofoam. Styrofoam is actually the trade name, Dow's trade name for expanded polystyrene. Ultimately, in all these applications, the ozone depleting substances eventually get released to the atmosphere. It doesn't matter how well your house is sealed. Studies show it takes about 2 to 3 years for CFCs released at ground level to drift up to the stratosphere and just start to cause the damage that I'm going to talk about in this lecture. This is an overview of the presentation today. I'm going to talk about some basic definitions and principles of stratospheric ozone depletion. Then I'm going to talk about the scientific basis and the scientific evidence. I'll talk about the environmental impact and the impact on the health of humans. And one of the mandates of this course is to talk about social implications, not just technical aspects. So I'm going to cover the political response to this environmental problem in substantial detail. There are some interesting parallels to the current climate change debate, if you want to call it that. The chemical industry and CFC manufacturers like DuPont initially tried to discredit the science and fought intensely against regulation of CFCs. Back in the 1980s, there were lots of stratospheric ozone depletion deniers. Of course, they weren't called that. It turned out that this is one of the rare environmental success stories. Despite significant industry opposition, in this particular case, science won the day. As you will see as I go through this presentation, scientists and engineers met the challenge and the world dodged a very big environmental bullet. It's an example of the world coming together, not just agreeing on a solution, but actually implementing that solution. And it's a model for global cooperation that we would like to see in dealing with climate change, for example. Before we get deeper into the material on stratospheric ozone depletion, I just want to refresh your memory on some basic terminology. This is a modified slide from the air pollution chapter. Remember, the atmosphere is divided into 5 layers, shown here. We live in the troposphere. On average, the troposphere is roughly 11 kilometers thick, so it goes from ground level to 11 kilometers. I should mention that it does vary a little bit with latitude. So if you're at the poles, the troposphere is thinner, and if you're at the equator, the troposphere is a bit thicker, but on average 0 to 11 kilometers. This is the layer, of course, where we live. It's the layer where most weather happens. Almost all clouds and precipitation happen in the troposphere. So most snow and rain are in the troposphere. The next layer up is the stratosphere. It ranges from about 11 to 50 kilometers. And the ozone layer is in the stratosphere. The ozone layer is a layer of O3 or ozone gas that provides UV protection. We'll get to how the ozone forms in this layer, but for now the key point is that this layer of ozone in the stratosphere provides protection against the sun's UV light. So it provides protection for the biosphere, or from a strictly human perspective, it protects us from getting sunburns and skin cancers and eye damage and the like. This is another refresher slide from Chapter 4. We talked about the electromagnetic spectrum in Chapter 4 when we were talking about thermal radiation. The purpose of this slide is to remind you about ultraviolet radiation, which is critical to today's discussion. This slide shows the full electromagnetic spectrum. So recall that at short wavelengths here we have gamma rays, very high energy gamma rays. Slightly longer wavelengths we have X-rays, then ultraviolet, then the visible spectrum, then infrared and microwaves and radio waves at the very long wavelength end of the spectrum. Recall that humans only see a small wavelength band. We only see the visible band here, a small wavelength band in here. UV light is just off the visible spectrum. Its wavelength is just a bit too short for humans to see. Apparently honeybees see UV light, but not people. Sometimes it's called black light. You can buy a black light in the store that gives off ultraviolet light. So a key point is that the shorter the wavelength the light has, the higher its energy. So UV light has more energy than visible light. That's why UV gives you a sunburn, but you don't get a sunburn from normal visible light. So ultraviolet light has a higher energy level. Its photons have a higher energy level, and that's a key point that we're going to come back to in this lecture, and that's critical to understanding stratospheric ozone depletion. Next, I want to talk about ozone, which is O3. This is a plot that shows the ozone concentration in the atmosphere with altitude. You could get this kind of plot by putting a ozone sensor in, for example, a weather balloon and measuring the ozone concentration as the balloon rises. So come over here on the vertical axis, we have altitude going from ground level up to 35 kilometers. And remember, the troposphere goes up to about 11 kilometers, depends a little bit on latitude. And above that we have the stratosphere. And then on the horizontal axis here we have the ozone concentration. Now ozone has the very unusual characteristic of being beneficial in the stratosphere, so up high, in that it protects us from ultraviolet radiation and protects the biosphere from ultraviolet radiation. But in the troposphere, down ground level, it's harmful. And we talked about ground level ozone, or so-called tropospheric ozone, in the air pollution chapter. In urban areas, nitrogen oxide, so NOx, primarily from combustion, plus UV light, so sunlight, plus volatile organic compounds combine to form this smog, O3, or ground level ozone. This is a type of photochemical smog. So don't confuse ground level ozone, which is smog, with stratospheric ozone. As you can see from this graph here, most of the ozone in the atmosphere is in the stratosphere. So about 90% in the stratosphere and about 10% in the troposphere, so-called ground level ozone. And unfortunately, the ozone levels have been falling in the stratosphere where we want ozone, primarily due to ozone depleting substances, particularly CFCs, and ozone levels have been rising in urban areas primarily because of combustion and of fossil fuels, largely associated with transportation. In this next slide, I'm going to get into some of the technical details. Stratospheric ozone levels are measured in something called Dobson units. This is a measure of all the ozone in the atmosphere above your head, so all the way between ground level and outer space. If all the overhead ozone was brought down to ground level and concentrated, it would form a layer just a few millimeters thick. And a Dobson unit is equal to a layer of ozone just equal to 1/100th of a millimeter at atmospheric pressure and 0 degrees C, so-called standard temperature and pressure. So at mid-latitudes, for example in Toronto, the ozone column is typically about 350 Dobson units, or about 3.5 millimeters if you brought all the ozone down to ground level. Now, you may have heard of the so-called ozone hole in Antarctica. It's quite famous, and we'll talk about it more in this lecture. In Antarctica in the spring, the ozone column drops below 100 Dobson units, forming the so-called ozone hole. Of course, it's not really a hole, it's just a decrease in the concentration of ozone in that area. So it drops to about 1/3 of its normal level, and we'll talk about why that happens later in this presentation. And since the 1970s, the measured UV levels in Antarctica during the spring, and in the spring that's September, October in the South Pole, the UV levels have been measured to increase by about 130%. And we're going to talk about why that's happening later in this lecture. While I'm on the topic, I thought I'd like to talk about the Antarctic ozone hole, which you maybe have heard about. The basic chemistry of stratospheric ozone depletion was actually predicted theoretically in 1974 by a couple of scientists at the University of California, Sherwood Rowland and Mario Molina. Their work appeared in the very prestigious scientific journal Nature. But the first strong physical evidence for stratospheric ozone was the measurement of the Antarctic ozone hole by the British Antarctic Survey in 1985. This picture shows the formation of the hole. Of course, as I mentioned, it's not really a hole, it's just a suppression of the total ozone column or ozone concentration in the atmosphere. The colors indicate Dobson units. The yellow color here is about 300, you can see from the scale, is around 350 Dobson units, which is about normal. The blue corresponds to 100 Dobson units. And so you can see the formation of the hole, which is this dark blue patch, and you can see it happens in this figure somewhere between 1981 and 1987. Of course, it was discovered in 1985, or first measured. And you can see from this graph that it's getting worse up to about 1999. Nowadays, this hole still forms during the Antarctic spring. At the time, in 1985, this discovery shocked the world, and having physical evidence spurred governments into real action. It led to what's called the Montreal Protocol on Ozone Depleting Substances. This was an international agreement initially involving 23 countries to cut emissions of CFCs and other ozone depleting substances. Next, I'm going to talk about some of the physical science and chemistry needed to understand stratospheric ozone depletion. Ozone is formed and destroyed in the stratosphere by what are called photochemical reactions, also called photolysis. Remember that UV light has more energy than visible light. It has a shorter wavelength. It has enough energy to break chemical bonds. Stratospheric ozone is formed by a pair of reactions that I'm going to talk about. In the first reaction shown here, diatomic oxygen, so a molecule of O2, is hit by UV light. Sometimes we call this a photon. A photon is a packet of light energy. This photon breaks the molecule up into two atoms, so oxygen atom and an oxygen atom. When a molecule is dissociated this way, in other words, when it's broken apart by light energy, by ultraviolet light, it's said to have undergone photolysis. So now we have two atoms of oxygen floating around rather than the original O2 molecule. So in the next reaction here, the atomic oxygen finds an O2 molecule and bonds with it to form ozone right here. And that's how ozone is formed in the stratosphere. I've got here a short video from NASA that shows this process and these two reactions. So let me just play this. So we can see the oxygen molecule getting hit by a photon, breaking apart, and then the atomic oxygen floating off and finding an O2 molecule to form O3. Let me play that again so you can just watch. And so this video depicts the two reactions shown on the left of this slide. This is how ozone is formed in the stratosphere, that protective layer that actually protects us from UV light. So now we've talked about how ozone is created in the stratosphere, but ozone is also destroyed by a similar process, also involving photolysis. So what we have here shown in this reaction is we have an ozone molecule being struck by ultraviolet light, so a UV photon as we call it, and that UV photon breaks the chemical bond and it dissociates or photodissociates the ozone into molecular oxygen and atomic oxygen. Now in this process, the ozone molecule actually absorbs that UV light energy. And so the absorption of that UV light energy by this photolytic reaction means that less of the UV energy reaches the ground. And that's actually the source or the beneficial shielding effect that we get from the stratospheric ozone layer. Again, here I've got a short video from NASA that demonstrates this process. So here we see in the center a ozone molecule being struck by a ultraviolet light photon and dissociating into atomic oxygen and molecular oxygen. And in the process, the UV photon is absorbed, providing the shielding effect. So far we've discussed natural reactions in the ozone layer. So you should have an understanding of how the ozone forms in the stratosphere and how it protects us from UV light. So at this point in the story, humans enter the picture. As we know, the concentrations of stratospheric ozone that protect us from the sun's UV rays are being depleted by man-made chemicals, mainly CFCs. The problem is mainly the chlorine in the CFCs. Now this gets a bit technical, so don't get too worried about the details. Just focus on the overall process. So what's going on here is the ozone destruction process involves three reactions. The first is photolysis, shown here. So we have a molecule of CFC11 getting hit by UV light, and that strips off, breaks the chemical bond of one of the chlorine atoms. So you end up with a free chlorine atom. This free chlorine atom acts like a catalyst. A catalyst is a substance that promotes a reaction but remains unchanged in the process. And you'll see that chlorine remains unchanged in this process. So what happens here, looking at this, is we have this chlorine atom that was freed by photolysis up here, and it actually reacts and destroys an ozone molecule. It creates something called chlorine monoxide and oxygen, but this chlorine monoxide here goes on to another reaction that frees the chlorine atom. Again, don't get too hung up on memorizing the details. The main points to remember here are the net result. One ozone molecule is destroyed, and through another reaction, the chlorine atom remains unchanged. It gets returned to its unbonded state. So the chlorine atom is free to repeat the cycle over and over again. Here's a short little video of the process. It's a little complicated, but it repeats itself over and over again, and we can watch it. So it sets off with a CFC molecule being hit by UV light and stripping off the chlorine. The chlorine then destroys an ozone molecule, and then through another reaction is freed. So the chlorine atom is free to repeat the cycle over and over again. And so you can watch this little video here. That video represents the three reactions on the left-hand side of the slide. So one chlorine atom in this way can react again and again, making the loop shown in this video tens of thousands of times, each time destroying an ozone molecule. So one chlorine atom that's stripped off a CFC can destroy tens of thousands of ozone molecules in the ozone layer. I should mention as a side point, there's a similar catalytic process for bromine, which has the symbol Br. So you'll see later on in this presentation that some of the ozone depleting substances like halons contain bromine instead of chlorine. So now that you have some understanding of the basic chemistry, I want to come back to the cause of the Antarctic ozone hole. Eventually, that free atomic chlorine that is destroying the ozone in a catalytic cycle reacts to form a less reactive compound. For example, here I've listed chlorine nitrate, but there are a few others. And so this binds up the chlorine atom and stops the catalytic cycle. But it turns out that the Antarctic has a unique weather phenomenon called the polar vortex, and I've shown a little animation here from satellite data from NASA. Because of the particular land and ocean formation at the South Pole, a highly isolated cell of spinning air forms. This is a whirling mass of extremely cold air, and it's largely isolated from the rest of the atmosphere. Remember, this is the winter time in Antarctica, so you have 24 hours without sunlight, and so this makes the air extremely cold, and it can get down to as low as minus 90 degrees C, and it's cold enough to form what are called polar stratospheric clouds. Normally clouds can't form in the stratosphere, it's too dry. Normally you only get clouds in the troposphere, but when it gets this cold, you can get clouds in the stratosphere. And these stratospheric clouds that are made up of ice crystals provide a platform for a series of chemical reactions that result in the formation of chlorine gas. So this chlorine nitrate up here, through these reactions, releases some of its chlorine in the form of chlorine gas. Now, when the sun rises in the springtime, that's October, that chlorine gas undergoes photolysis. So the chlorine gas gets struck by a UV photon and forms, again, we get back to this atomic chlorine, and this atomic chlorine reinitiates the catalytic destruction of ozone that we talked about in the previous slide, and that starts the cycle up again. And that's the reason for the ozone hole in the spring and why we get this sudden depression of ozone concentration in the springtime. The polar vortex happens in the North Pole, but the weather in the North Pole is such that the rotation of the air is not so well isolated. It doesn't get that cold, and so we don't see similar hole in the ozone layer forming over the North Pole. This slide shows the actual formation of the hole in terms of measurements. These are measurements of the ozone concentration with altitude over the South Pole. As I said, they could be obtained. I think these are obtained with a weather balloon. So what we have here is altitude going from ground level up to 35 kilometers, and on the horizontal axis we have what's called partial pressure of ozone, but just think of it as ozone concentration. And this graph shows the very rapid thinning or destruction of the ozone layer in the springtime. This is in Antarctica. And so this first curve here is the ozone concentration in the dead of winter. So before the sun has risen. This is August, where we have 24-hour night, and you can see the strong concentration of ozone at high altitude. These other curves here are just a short time later, just a couple of months later in the spring, where we have sunrise. And when we get sunrise, for part of the day, sunrise causes the photolytic production of atomic chlorine. And remember that atomic chlorine drives the destruction of ozone over the pole. So this shows the dramatic formation of the so-called ozone hole. This graph shows the measured springtime minimum ozone level measured in Dobson units over Antarctica. This is, if you like, the sort of depth of the ozone hole every year. The data is taken from the NASA website. So what we have is the minimum ozone level that happens in the springtime, as we just talked about, versus year going from 1980 to almost the present time. These are satellite measurements, and TOMS here is NASA's total ozone mapping spectrometer. As you can see, there are seasonal fluctuations in the minimum level. This is due to weather. For example, the minimum level would depend upon how well the polar vortex forms and how long it persists in a given year. But even with the fluctuations, you can see that there's some evidence of recovery since about the year 2000. And the good news here, in fact, NASA modeling based on the banning of ozone depleting substances now predicts a full recovery of the ozone layer to 1980 levels by about 2070. And I'll show you some more results later in this presentation. This is very good news indeed. So far I've talked mainly about CFCs, but there are several other classes of ozone depleting substances that you should be aware of. This table shows some of the other substances. The common factor is that ozone depleting substances contain either chlorine or bromine. Both chlorine and bromine cause the catalytic reaction that destroys ozone, as I discussed earlier in this lecture. So we have CFCs first here. You're aware of these, chlorofluorocarbons. They were invented in the 1930s. They're non-toxic, non-reactive, non-flammable. When they were first invented, they were thought to be environmentally benign. Because they're inert, they have very long atmospheric lifetimes. And over in this column, you can see they have atmospheric lifetimes of 50 and 102 years for CFC 11 and 12. Because they're inert, they have very long atmospheric lifetimes. The only removal mechanism is photolysis, which occurs after the chemicals drift up into the stratosphere, which takes a couple of years. Another class of ozone-depleting substances is HCFCs, or hydrofluorocarbons. Hydrofluorocarbons were the first replacements for CFCs. Hydrogen was added to the CFC molecule basically to make them more reactive, so they were no longer as chemically inert. You'll notice they have much shorter atmospheric lifetimes over here, you can see, right? So this means that they would be destroyed, that HCFC molecules will be destroyed by chemical reactions in the troposphere and do less damage to the ozone layer. Another class of ozone depleting substances is halons. Like CFCs, they also have long atmospheric lifetimes. They're highly unreactive, but these chemicals contain bromine, which destroys ozone in a catalytic reaction similar to chlorine. Halons used to be used in fire extinguishers and are now banned. There are other ozone depleting substances as well, such as carbon tetrachloride. Nowadays, chemicals are rated based on their ozone depletion potential, or ODP. This is a measure of how much they destroy stratospheric ozone. The reference gas for ODP is CFC11. In other words, the amount of ozone destruction per kilogram of substance relative to CFC11. So if you look on this table here for CFC11, you'll see its chemical formula, and by definition, it has an ozone depletion of 1. So it's the reference standard. In comparison, if you look down here at halon, which is used in fire extinguishers, halon 1301, it has a ozone depletion potential of 13, meaning if you release 1 kilogram of this substance into the atmosphere, it'll destroy 13 times more stratospheric ozone than 1 kilogram of CFC11. In fact, I still have a halon 1301 fire extinguisher in my kitchen, which I bought in the late 1990s. These were banned from sale worldwide in 2000. Amazingly, it's still fully charged, and when I replace it, I'm going to have to be careful to make sure that I dispose of it correctly so that the halon's not released to the atmosphere. Okay, let's look at some of the other ozone depleting substances. On the previous slide, we discussed HCFCs, hydrochlorofluorocarbons, which were the first replacement refrigerants for CFCs. And here on this table, we have HCFC22. And you can see, as I discussed, they added hydrogen to the molecular structure. That makes it more reactive, and if it's more likely to react, it has a much shorter atmospheric lifetime. HCFC has an atmospheric lifetime about 25 times less than CFC11. And so it's going to react in the troposphere and do less damage in the stratosphere. The next generation of refrigerants which we're currently using are hydrofluorocarbons, or HFCs here. And here I've got a common one is HFC 134A. These are currently in very widespread use. The Coke machine down the hall likely uses R134A and HFC. My Honda Civic uses R134A for its air conditioner. These refrigerants are ozone friendly. They have no chlorine, as you can see in their chemical structure here. So they have a ozone depletion potential of essentially 0. I don't know why it's 5 times 10 to the minus 4. There must be some exotic reaction that goes on, but it's essentially 0. But the problem is these HFCs have very high global warming potentials. For example, R134A is about 4,000 times worse than carbon dioxide in terms of blocking infrared radiation. I'll come back to this issue at the end of this presentation. Next, I'd like to talk about worldwide ozone depletion. Everyone talks about the Antarctic ozone hole because it's such a dramatic visual illustration of stratospheric ozone depletion. But it's important to remember that ozone depleting substances that we saw on the previous slide are causing the ozone column to decrease worldwide. This image shows the ozone column over North America measured from satellites. In Toronto, we're at a ozone level of about 350 to 400 Dobson units, so right in about here you can see, which isn't too bad. But in the 1980s and 1990s, these concentrations were falling quite rapidly worldwide. Of course, this has an impact on the biosphere. The main impacts of higher UV levels from a human perspective are skin cancer, cataracts, eye damage, and other health problems. Increased exposure to UV has been linked to immune system suppression. In terms of health impacts on humans, the medical literature shows that solar radiation is probably the main cause of all skin cancers. There are two main categories of skin cancer: non-melanoma, which is quite common but rarely fatal, and malignant melanoma, which can be life-threatening. Epidemiological studies show that there's a direct link between skin cancer and UV exposure. Epidemiological studies look at where populations live and how much UV they're exposed to. These studies show that if you live at lower latitudes, so if you live closer to the equator, you get more exposure to UV and skin cancer rates increase. The medical literature estimates that about a 1% increase in UVB exposure will cause about a 0.5% increase in melanoma and about a 2.5% increase in non-melanoma. Now, we haven't talked about this, but the UV spectrum can be broken up into segments, and UVB is the shorter wavelength part of the UV spectrum. It has more energy and does more damage than the UVA part of the UV spectrum. In North America, we've been seeing increased skin cancer rates. Melanoma among fair-skinned individuals is increasing at about 2 to 3% per year in the United States. But you have to keep in mind that ozone depletion is a relatively new phenomenon. Skin cancer rates have a very long latency period, often more than 20 years, so it's difficult to directly link increased skin cancer rates to stratospheric ozone depletion. Some or all of the increase in skin cancer rates could be lifestyle related. People nowadays are spending more time outdoors. In any event, Canada introduced the UV index in 1992 in part because of concern over stratospheric ozone depletion and rising skin cancer rates. Of course, the effects of increased UV levels would not just affect humans. They also have an impact on the biosphere. For example, it's been shown in the lab that amphibian eggs cannot withstand higher levels of UVB. It's suspected that the worldwide decline in frog and toad populations may in part be due to the thinning of the ozone layer. As I mentioned in the introduction, it's important to cover the social implications of environmental issues, not just the science. In many cases, the political response has more influence than the scientific response on whether we solve a global environmental issue. Also, this is such a good news story, I want to talk about it in some detail. It starts with the invention of CFCs in the late 1920s. Manufacturing and wide use of CFCs started in about the 1930s. These man-made molecules were initially thought to be benign. Then in 1974, two scientists from the University of California, Mario Molina and Sherwood Rowland, published a paper in the journal Nature saying that CFCs were a threat to the stratospheric ozone layer. They outlined the basic photochemistry that we've talked about in the previous slides. As you might expect, the CFC industry fought intensely against regulation. DuPont was a major manufacturer of CFCs at the time, and the chairman of the board of DuPont called Molina's and Rowland's theory utter nonsense and a science fiction tale. But despite the pushback from industry, in 1979, the United States, Canada, and Scandinavia banned non-essential aerosol spray can propellants. At the time, these countries were world leaders. They acted to safeguard the environment, and furthermore, they enacted regulations even though industry was complaining loudly that the science was not settled. In retrospect, as you will see, it was a good thing that we did. Prior to 1979, CFCs were used in most aerosol sprays. Over 50% of North American production of CFCs was for things like hairspray, deodorants, spray paint, even silly string. As I mentioned, in 1979, the USA, Canada, and Scandinavia banned CFCs for non-essential aerosol propellant use, but most countries continued to manufacture CFCs. Then came the game changer. In 1985, the Antarctic ozone hole was discovered by the British Antarctic Survey, and this dramatic evidence really awakened the world. This led to the 1987 Montreal Protocol on substances that deplete the ozone layer, where 23 nations agreed to a 50% reduction in the manufacture of CFCs by 1999. Subsequent measurements of the ozone layer showed that it was declining quickly and that the agreements at the Montreal Protocol were not going to be sufficient. And so there were subsequent meetings, the 1990 London Amendments, where 93 nations agreed for phasing out CFCs, most halons, and carbon tetrachloride by the year 2000. There were further amendments in 1992 where they moved up the phasing out of CFCs and carbon tetrachloride to 1996. This amendment also called for phasing out most of these hydrochlorofluorocarbons by 2003, although there are some that are allowed until 2030. And then in 1995, Mario Molina, Sherwood Rowland, along with a third scientist, Paul Crutzen, won the Nobel Prize in Chemistry for their pioneering work describing the photochemistry of stratospheric ozone depletion. This graph shows the concentration of a couple of CFCs in the atmosphere, CFC 12 and CFC 11. As I mentioned, the worldwide production of CFCs ended in 1996, and you can see the concentrations that were rising until the late 1990s have now started to fall. Of course, the recovery is going to be very slow as these chemicals have long atmospheric lifetimes, but nevertheless you can see that the Montreal Protocol with subsequent amendments is quite an amazing environmental success story. It's also a model of international cooperation and real action, the kind we'd like to see on environmental problems like climate change. I thought I'd also show you some recent results from NASA. These are modeling results of the recovery of the Antarctic ozone hole. So on the vertical axis here we have Dobson units, and on the horizontal axis we have the Antarctic ozone hole minimum going from 1960 up until the end of this century. The white dots are actual measurements that I showed you earlier, and the red curve here is the NASA simulations of the recovery of the ozone hole, so the minimum value expected in the springtime over time, and you can see that it's expected to recover by the end of this current century. I'd also like to show some recent NASA projections of the stratospheric ozone concentrations worldwide if no action had been taken. Now what I have here is a little GIF, and you'll notice up in the top corner here is the year, starting in 1974. And the color coding is, of course, Dobson units, with dark blue being less than 100 Dobson units. And you'll see this cycle around. And by 2060, we have near complete destruction of the stratospheric ozone layer. That is less than 100 Dobson units worldwide. So this is what would have happened if we hadn't taken action on CFCs and other ozone depleting substances. So by so doing, we've avoided untold damage to the ecosphere. In addition, we've avoided enormous impacts on human health. According to the United Nations Environmental Program, we've avoided 180 million cases of skin cancer, 1.6 million deaths, and 45 million cases of cataract just in the US. And this is one of my favorite graphs. It's not very colorful, but you get the idea. On the vertical axis, we have excess skin cancers, so skin cancers that happen because of the increased UV, and these are in per million people per year against year on the horizontal axis. And the first curve here is no restriction if we had taken no action, and you can see the number of skin cancers skyrocketing. The next curve is the Montreal Protocol, the first agreement to limit CFC production, and then the subsequent amendments that took stronger action, the London Amendments, the Copenhagen Amendments, and the Montreal Amendments. Now, the United Nations Environmental Program estimates that the cost of these replacement measures for refrigerants and other uses of ozone depleting substances to be about $235 billion US. But the economic benefit outweighs this, according to the UNEP. Because of reduced damage to fisheries, agriculture, and materials, the UNEP estimates that the economic benefit of phasing out CFCs is about 2 times its cost, not including healthcare costs, amazingly. So it was certainly in our best interest to take action on this problem. This is normally where the lecture ends, but I have a very recent update. In October 2016, just a few months ago, at least when this video was recorded, there was another meeting of the nations under the Montreal Protocol, this time in Kigali, Rwanda. 170 nations made commitments to phase out hydrofluorocarbons, HFCs, under the Montreal Protocol, and they agreed to a legally binding timetable to replace HFCs with more environmentally friendly alternatives, and agreed to trade sanctions on nations that do not comply. One of the more common HFCs is R134A, and as you can see from the graph, the concentration of HFC 134A is rising while CFCs are falling. When this news was announced in the news, there was a lot of confusion in social media. I mean, HFCs are already ozone friendly, aren't they? So why must they be phased out? They don't contain chlorine, they don't contain bromine, so they don't destroy ozone. So what's going on here? Well, the answer is that HFCs have very high global warming potentials. I mentioned this earlier in this presentation. For example, R134A, which is a hydrofluorocarbon, it's ozone friendly, but it has a global warming potential of 4,000. That means it's 4,000 times worse than CO2 in terms of blocking infrared radiation. So 1 kilogram of R134A is equal to discharging 4,000 kilograms of CO2. I should mention that there are alternatives already available that have both low ozone depleting potential and a low global warming potential. One example is Honeywell's HFO 1234YF, which meets both of those criteria. One of the issues with these alternative refrigerants to HFCs is that they tend to be flammable, so there's a slight safety trade-off. But this is an area of very active research. The Kigali Agreement is particularly interesting because it's separate from the 2016 Paris Agreements on climate change, even though it deals fundamentally with a refrigerant, with a gas that's causing climate change and not causing ozone depletion. I thought I'd end with a little bit of uninformed silliness from President Trump.
Give me a mirror. But no, in the old days, you put the hairspray on, it was good. Today, you put the hairspray on, it's good for 12 minutes, right? But, you know, they say that you can't. I said, wait a minute. So if I take hairspray, and if I spray it in my apartment, which is all sealed, and you're telling me that affects the ozone layer? Yes. I say, no way, folks. No way. Okay? No way.